welcome back to the part 2 of determine the unknown capacitance of the capacitor. If you haven't watched the part 1, please watch it, since I introduced the problem concept and also the method how to derive the capacitance in the time domain. And this is the part 2 where I do the calculation in the frequency domain, the second method. And even though it looks a little bit complex, but actually if you look at here, this is a very familiar formula for every electrical engineer, where we have the impedance of the capacitance equal to the voltage of the capacitor in the frequency domain over or divided by the current going through the capacitor in the frequency domain. And those two steps I just show to give the derivation feeling to the very familiar formula. So the brief introduction is that first they will do the Fourier transformation on the voltage of the capacitance in the time domain, and also the Fourier transformation of the current on the capacitance in the time domain, and then we obtain the voltage of the capacitance in the frequency domain and also the current of the capacitance in the frequency domain. After that, they will also look at the relation between the voltage of the capacitor and the current of the capacitor in the time domain. If you want to understand this derivation, please refer to my part 1 also. I already explained how can we got this kind of relation between the voltage of the capacitor and the current of the capacitor in the time domain. Okay, after the step 1, they will utilize two properties of the Fourier transformation. The first property is the linear property of the Fourier transformation, and the second property is the corresponding result between the result of derivative in time domain and in frequency domain. When we do the derivation of a, let's say, of a function in the time domain, what would be the result in the frequency domain after Fourier transformation? And this is what we could obtain. And with this obtained result, we do some mathematical transformation, and then we go back to the very familiar formula for electrical engineer. And with this formula, we will start to calculate this formula in the log scale, and also taking into account only the magnitude. And after that, when we have the magnitude of the voltage on the capacitor at a specific frequency and also the magnitude of the current through the capacitor at the corresponding frequency, we can easily calculate our capacitance, since we already know the frequency. So for sure we will know the angular frequency W also. And this one, and this one, both of them can be obtained from the Fourier transform of our measured signal, our measured voltage signal and the current signal. Now I will demonstrate it in the LTSpice about how to apply this theoretical method to calculate the capacitance or to determine the unknown capacitance. Here's our LTSpice demonstration. Okay, one more time. If you haven't known how to create such a circuit or how to read those parameters like pulse, transient, please refer to my previous videos about LTSpice. I have introduced all of them. But in this case, we will focus only to demonstrate how to apply the theoretical method of calculation to determine the capacitance in frequency domain. And one more time, as a reminder, here we need to apply 1 farad to the capacitor in order to simulate the result of the voltage and also the current going through the capacitor. But when we already got the measured voltage on the capacitor and the current, we will assume that we don't know the capacitance here is 1 farad. And then based on the measured voltage on the capacitor and also the current going through the capacitor, together with the calculation method in frequency domain, we will start to derive the capacitance of this capacitor C1 is around or approximately 1 farad. So now let's run the simulation in the time domain. Now we need to measure the voltage on the capacitor as if like we were doing the real experiment on the capacitor in order to determine the capacitance of this unknown capacitor. Of course, we can see this is 1 farad, but please just imagine that we don't know this is 1 farad. Now measure the voltage on the capacitor. And this is the voltage on the capacitor, and then we will need to measure the current going through the capacitor itself. We will add another plot, and here in this plot we need to click on that plot and click back to our schematic, press Alt key and measure the current going through the capacitance. Now I put the formula how to calculate the capacitance in the frequency domain over here, so we can easily know what are the parameters we need to determine from the measurement in order to determine our capacitance. So now we need to know the voltage in the frequency domain at a specific frequency. And if you can look at the pulse here, or maybe we can right click on the voltage source and we will see. So this is the period of a pulse signal. The period is 0.02 second, so the frequency of our square signal or the pulse signal is 50 Hz. That's why we can easily choose the frequency where we want to measure our voltage in the frequency domain is 50 Hz. And also at 50 Hz we need to get the measurement of the current in the frequency domain. And from those two, together with the information that we obtain, those two information at 50 Hz, together with this formula, we will calculate our capacitance or to derive our capacitance. Now, in order to obtain the value of the voltage in the frequency domain at a specific frequency, we need to do the Fourier transformation. And the algorithm in order to do the Fourier transformation on the voltage in LTSpice will be FFT. We can easily do the same thing, FFT, for a signal in Python. So for example, this is your real measurement setup. And then you have a record of your voltage in the time domain. And also the record of your current in the time domain, somehow similar like this, into two files. You can import those two files into your Python code. In the Python code, you can use the SciPy, or you can use some built-in library from Python to apply the FFT algorithm in order to obtain the frequency domain of those two signals. But here we already have the FFT algorithm built in our LTSpice. We just need to apply it. So here I would choose on my, I click on here. I can go back to the, now I go back here. I will apply my FFT on the voltage first. Right click and we choose view, we choose FFT, and we choose our voltage, which is of course VN001. You can see the name of our signal. Apply FFT to this signal. And here is the frequency domain of our voltage. And as we say, we want to measure our voltage in frequency domain at 50 Hz since the fundamental frequency of our pulse signal voltage is 50 Hz based on the period of the pulse. Now I will right click, choose a cursor. Let's say just one cursor is enough. And I move to 50 Hz. Of course, it should be somewhere here. Now, I think this one is reasonable. Frequency is 50 Hz, approximately 50 Hz. Or maybe we can just move a little bit more accurate. Yes. Okay, now it's more closer to 50 Hz. And the magnitude of our frequency, the magnitude of our voltage here is, let's write down -7 dB or -7.13 dB for the magnitude of the voltage at frequency 50 Hz in the log scale will be minus 7.13 dB. Now we obtain our voltage. We need to have the corresponding value of our current at the same frequency, also in log scale. Now let's close it, and then we applied the right click again, apply FFT on our current signal, which is IC1 here, IC1. Click OK, and here is our signal in frequency domain of the current. Again, we will measure the magnitude of our current at frequency equal to 50 Hz. So here, this is the frequency at 50 Hz, I guess. Yes, 50.2, close to 50 Hz, that's good. And the magnitude of our current at frequency in log scale, at frequency 50 Hz in log scale is 42.62 dB. Now we already have enough information to calculate our capacitance based on the formula, right? We just need to apply it. And our final calculation of the capacitance is equal to 0.976 farad. And if we're gonna make the rounding, 0.976 approximately like 1 farad, right? 1 farad. So the correctness of the method to calculate the unknown capacitance in frequency domain is correct. And another advantage is that we don't have to calculate the signal at 50 Hz. We can choose other signal. We can choose another frequency, and then we can still calculate our capacitance. For example, now let's choose another frequency, and we will somehow obtain the approximate capacitance. And I will apply the FFT again in our voltage. And I will take one cursor to measure. For example, here of course we have a peak. It means we have some signal. So we better choose a peak in order to have some signal to calculate. Don't choose something like down here. That's noise. Now at this signal, we can make it this signal. With the signal of the voltage at the frequency, let's say approximately like 150 Hz. So that will be our interest frequency, where we will start to derive our capacitance. We read that the magnitude of our voltage at that frequency, 150 Hz, in dB is equal to minus 17.58 dB. And now we need to do the FFT for our current and also measure the current value or the current magnitude at the same frequency, 150 Hz. I close it, and I will do the FFT on the current. And I will use a cursor again to measure. And because we measure the voltage at frequency of 150 Hz, so we have to measure the current also at 150 Hz. Here we will read out the value of our current in magnitude, which is 42.38 dB, and apply with the formula together with the information at the frequency 150 Hz, we can derive our capacitance. One more time. And now in the case of frequency of interest is 150 Hz, we obtain the capacitance around 1.056. And of course 1.056 farad, somehow close to 1 farad. Yes, and that's the end of the demonstration how to use the second method to derive our capacitance in frequency domain. And I prefer the frequency domain since It's straightforward. There's no need for integration, only subtraction, division. Oh, that's it. Thank you so much for watching. Thank you. See you again in another video. Goodbye.